Hello everyone, welcome back to the tutorials again. So you can see in previous session we have discussed about the analysis of pre-stressed concrete member. So in today's session we are going to uh, discuss about how to analyze the pre-stressed concrete member, what are the notations which we are going to use. If time permits, we are going to move to the problems on pre-stressed concrete. So you can see over here, the stresses due to pre-stressing alone are generally combined stresses due to. So whatever the pre-stressing forces are there, due to pre-stressing are combination of stresses due to direct load and bending resulting from eccentricity applied eccentrically applied load. The stresses in concrete are evaluated by using the well-known relation from combined stresses used in case of columns. Okay, so what this particular paragraph means, this particular paragraph means the following notations and signs. This paragraph means the pre-stressing stress is due to not only due to the load which we are applying. Okay, so it is due to the combined effect of direct loading and due to eccentricity there is some amount of movement which is going to get induced. Okay, so due to that also it is going to happen. Okay, so we came to know about the stresses induced as a pre-stressing is combination of various loads. Okay, so following are the notations are signed conventional signs used for analysis of pre-stress. First one, P is used for pre-stressing force, positive when producing the direct compression. So notation will be like this: positive, the load will be considered as positive and it is producing the direct compression. Small e is eccentricity of pre-stressing force. So m is p into e, that is force into e. So a capital A is cross sectional area of concrete member. I is second moment of area of section about its centroid, and ZT and ZB is equal to section modulus of top and bottom fibers. So F superior, F inferior, that means pre-stress in concrete developed at top fiber, superior means top, inferior means bottom fibers, positive when compression, negative when tension in nature. YT and YB distances of top and bottom fibers from centroid of the section. Small I is radius of gyration. So it is very simple to understand. So first let us understand the formulas. Now when there is no eccentricity, in that case consider the concrete beam with concentric tendon. So tendon is acting exactly at the centroid. That means concentric tendon. In that case, uniform pre-stress in a concrete is going to get distributed. So which is equal to pre-stressing force divided by capital A, that is cross-sectional area. Which is compressive across the depth of the beam, which is compressive across the depth of the beam. Generally, applied loads and the dead load of the beam induce tensile stresses. This is very important point which you have to note. So the whatever the pre-stressing force is there, that is going to induce the force in compressive nature, but the loads which are applied and dead load are in the beam are going to induce tensile stresses towards the soffit, are counterbalanced more effectively by eccentric tendons. So as these uh, loads are inducing the tensile stresses, to counteract these tensile stresses means there will be increase in length, that means there will be bending. So to bending means it is a tensile stress. So to counteract that, more effective way is to provide the eccentric tendon. So the meaning of that is eccentric tendon. Okay, so we will see further. You can see over here. Okay, now we have understood that the more effective way of placing the tendons is eccentrically placed tendons. Now let us see about the eccentric tendons. So figure 4.2, so this figure shows us about the eccentric tendon which is at a distance E from the centroid, which is at a distance E from the centroid. So which we are going to apply, load which we are going to apply is at a distance E. Now you can see here, mm, if we are going to apply the tendon at some eccentricity E, then what are the stresses which are going to develop as a pre-stressing forces are you can see over here the regular pre-stressing force, that is P divided by A, plus the moment which is going to get induced due to the eccentricity. So that can be better understood by this particular figure. So cross section is like this. Direct stress if we are going to apply, that is P by A. Bending stresses, that is PE divided by ZB. So the at top, at bottom we are going to study later, but just due to bending stresses and combining to these two, the resultant stress which is going to act on as a pre-stressing force. This is a resultant force which is going to act as a pre-stressing force. Now you can see, if we are going to consider this bending stresses, uh, at the top there will be a tension zone, at the bottom there will be a compression zone. At the top there is a tension zone, at the bottom there is a compression zone. What it says, tension zone means the zone in which length increases, and compression zone means the zone in which length decreases. That means whatever this beam is there, this beam is going to bend in this manner. This beam is going to bend in this particular manner. That is why topmost fibers are going to face the tension and bottommost fibers are going to face the compression. So bottommost is positive, topmost is negative. So if I want to find out the pre-stressing force at topmost fiber, then P divided by A minus sign is there because it is going to induce the tension. P divided by ZT. At bottommost fiber we are going to add this particular quantity, that is PE divided by ZB. So this is about the eccentric pre-stressing. So combiningly you can see at top fibers, if we want to calculate uh, at top fibers means F superior, P divided by E minus P into E divided by ZT. So if we elaborate it and if we take P divided by A as a common, it is going to give us P divided by A into 1 minus E into IT divided by I square. So don't worry about this, we are going to use this formula itself. So it is about the pre-stressing force at topmost fiber. Similarly, you can see pre-stressing force at bottommost fiber, that is P divided by A plus PE divided by ZB at bottommost fiber. So this is the formula which we are going to get. Now what we have studied till now is when the tendon is concentric and when the tendon is eccentric. But how about the dead load of this particular member, and how about the external load which we are going to apply? Though these two parameters are also going to induce the stresses in the beams. So let us study about those parameters further. So you can see over here resultant stresses at a section due to the dead load and live load. So you can see the concrete beam as shown in the figure supports uniformly distributed live load. So you can see distributed live and dead loads of intensity Q and G. So live load is Q, dead load is G. The beam is, dead load means self weight of the beam. The beam is pre-stressed by straight tendon carrying a pre-stressing force P. P is a pre-stressing force at an eccentricity E. So both first, this case is covered now. This case is covered at a eccentricity E. The resultant stress in concrete at any section are obtained by superposing the effect. Superposing the effect means effect of this particular pre-stressing force plus effect of this eccentricity plus effect of this external applied live load and effect of this self weight. So all together, if we combine our principle of superposition, hope you know the principle of superposition, by using that we can produce the final effect. So superposing the effects of pre-stress and flexural stresses uh, due to the loads, if m due to the loads, so we are going to get the final resultant forces by superposing. Now if mq and mg are live load and dead load movements, so due to live load and dead load there are some movements which are going to cause. Mq is, if it is uniformly distributed, it is ql square divided by 8, we call it as wl square by 8 as it is a uniformly distributed. Similarly, mg is gl square divided by 8, g is a self weight. So due to the live load and dead load, what is going to happen? Let us study. So due to live load as well as dead load, beam is going to bend in this manner. Beam is going to bend in this manner. Due to eccentricity, beam is going to bend in this manner. But due to dead load and live load, beam is going to bend in this particular manner. So topmost fibers will be under compression. If the beam is going to bend like this, topmost fibers will be under compression and bottommost fibers will be under tension. Because at the bottom you can draw the figure by yourself so that you can observe it. So take a rectangular beam, mark a centroid. So you can see like this, if I draw a beam and from here if I draw the beam in this manner, I can combine it. So topmost fibers will be under compression and bottommost will be under tension. If under compression, we are going to consider it as a positive. If under tension, we are going to consider it as a negative. So top positive, bottom negative, compression positive, tension negative. So you can see mg divided by zt at top, mg divided by zb at the bottom, mq divided by zt at the top, mq divided by zb at the bottom. So these are the stress distribution diagrams. So finally you can see this is the effect due to pre-stressing force, this is the effect due to eccentricity, this is the effect due to dead load, this is the effect due to live load. So P divided by A minus PE divided by ZT plus mg divided by zt plus mq divided by zt. So this is the resultant pre-stressing force at the topmost fiber. Similarly, this is the resultant pre-stressing force at bottommost fiber, in which P divided by A plus PE divided by ZB minus mg divided by ZB minus mq divided by ZB are combined together. So this is the stress distribution due to pre-stressing force having some eccentricity applied with live load considered with dead load as well. So all the loads, all the forces we have considered over here. So finally I can write the formulas like this. So F superior means at topmost fiber, F inferior means at bottommost fiber. So P divided by A minus PE divided by ZT plus mg divided by ZT plus mq divided by ZT is going to give us the stresses at topmost fiber. Similarly, this formula is going to give us the stresses at bottommost fiber at any section. So in case of pre-stressed member, the cross-sectional area of high tensile steel being a very small percentage of total concrete area, the stresses computation are based on the normal concrete cross-sectional properties. The use of equivalent concrete section all through important in interpreting test results experiments. So interpretation of these results are very important. As you can see in a beam, if I want to consider the cross-sectional area, let us consider the beam is of 230 by 450. So if I multiply 230 mm by 450 mm, I am going to get the cross-sectional area. But that is not the actual cross-sectional area of concrete, because there are some steel or strands or some strands or some wires which we are going to induce. So those cross-sectional area of those wires also to be subtracted from the total area to get the area of concrete. But as the cross-sectional area of wires or strands are very small, we are going to neglect it. That's what they are saying here. So first one, you can see, let us study the example, first example. So before moving to the first example, let us study one example from the notes. So let us study an example. Okay, so just a second. Okay, now this is the first example. First one, a rectangular concrete beam 100 mm wide by 250 mm deep. Spacing of beam is 8 meter, is pre-stressed by a strand cable carrying an effective pre-stressing force of 250 kilonewton located at an eccentricity of 40 mm. The beam supports a live load of 1.2 kilonewton meter. So live load they have given the eccentricity, even they have given the pre-stressing force, they have given the cross-sectional area, even they have given the length of the beam. Now calculate the resultant stresses distribution for the center of the span. Cross-sectional area of beam is assuming by considering this much density. Find the magnitude of pre-stressing force with eccentricity of 50 mm which can balance the stresses due to live load and dead load at the socket of the center span. So let us try to understand this. This is a beam which is applied with the pre-stressing force P. So pre-stressing force P they have given as 250 kilonewton. So P 250 kilonewton is applied at an eccentricity of 40 mm. Total length of beam is 8 meter, breadth of beam is 100 mm, depth of beam is 250 mm, and it is carrying the live load of 1.2 kilonewton per meter. So all these things they have given. Next thing what we have to do is we have to calculate the resultant stresses at the center of the span, means top fiber and bottom fiber. Magnitude of pre-stressing force with eccentricity E is equal to 0. E is equal to 40 mm. So what they are saying in case 2 is we need to find out the magnitude of pre-stressing force, that is P, at eccentricity 40 mm, so that the entire resultant is nullified. When we apply the live load, when we consider the dead load, whatever the results due to live and dead load are there, those live and dead loads should be counteracted. Like that P we have to apply, and that P they are asking us to find out. Okay, so we know about these formulas, we have discussed previously. So these are the formulas, you just go through these formulas. So just this example I have taken to make you understand about the data which they are going to give. Okay, so what we are going to do in next session, we are going to discuss about the example in detail. This example only I am going to consider, and we are going to solve this particular example in next session. So before that, make sure that you understood the stress distribution properly, make sure that you understood these formulas properly, and just try to remember this formula so that we can solve the examples easily. Thank you. We'll move further in next session.